Welcome to The Explainer. Today, we're winding the clock way, way back, all the way to the beginning. We're talking about the simplest form of a neural network you can imagine, the perceptron. This thing, it's pretty much the granddaddy of the AI we see everywhere today.
So when you hear the term machine learning, what comes to mind? Probably some crazy complex math, right? Lines and lines of code that look impossible to decipher? But what if I told you the whole core concept? The big idea behind it all is actually so simple you could explain it with a kid's story.
And you know what? To prove it, that's exactly what we're gonna do. Let's dive into a story. It's about this little monkey who's lost his mom. And a super helpful, though, let's be honest, kind of confused at first, butterfly.
Okay, so here's how the story kicks off. The butterfly says, "Hey, I can help." The monkey, he gives just one tiny clue. She's big. So the butterfly, working with only that one piece of information, makes its very first guess and, well, it leads the monkey straight to an elephant.
Right away, the monkey's like, no, that's an elephant. He gives immediate feedback. The butterfly's guess, totally wrong. And right there, that simple little loop, you make a guess, you get it wrong, and you get told why it's wrong. That, my friends, is the absolute heart of machine learning.
All right, let's break this down, because this little story isn't just for fun. It actually holds the three key building blocks we need to teach a machine anything at all. If we look closely at how our butterfly is learning, we can figure out exactly how to set up information so that an algorithm, our digital butterfly, can actually make sense of it.
First up, we need something called features. And don't let the name fool you, it's super simple. Features are just the different properties of a thing. So for our animals, the features could be stuff like, is it big? Does it have a tail? Does it have a trunk? These are basically the clues our machine is going to use to figure things out.
Okay, second thing we need, a label. The label is just the right answer. It's the ground truth that we're trying to teach the machine. In our story, it's really simple, right? There are only two labels. Is my mom, or, you guessed it, is not my mom.
So what do we do with all these features and labels? Well, we organize them into what's called training data. See, we can take all that stuff from the story and just pop it into a simple table. We turn words into numbers, like a 1 for yes and a 0 for no. And just like that, we've got a nice structured format that a computer can actually read and start learning from.
All right, we've got our data all set up. Now we need a brain for our digital butterfly. So let's bring in the star of the show, the algorithm that's going to do the learning. Meet the Perceptron.
This thing was actually invented way back in the 1950s. And the whole idea was to create a computer model of a single biological brain cell, a neuron. Its entire job, its whole purpose, is to look at some information and make a super simple decision. Yes or no. That's it.
So how does it actually make that decision? Well, it's kind of like a little checklist. It looks at all the features, like is big or has trunk, and for each one, it multiplies it by something called a weight. Think of the weight as how important the perceptron thinks that clue is. Then it just adds all those up, adds one final little number called a bias to kind of nudge the result, and that's it. If the final score is positive, it shouts yes. If not, it says no. But here's the really cool part, how it learns. The perceptron is all about what we call error-driven learning. And it means exactly what it sounds like. If the machine gets the answer right, it does absolutely nothing. It only changes its thinking. It only adjusts those internal weights when it gets something wrong. And the way it updates itself is incredibly simple. Let's say it predicts no, but the right answer was yes. All it does is tweak its weights a little bit to make a yes answer just a little more likely for next time. And if it guesses yes when it should have been no, you guessed it. It does the exact opposite. It just nudges the weights in the other direction. We can actually picture this whole process. Imagine we plot all our animal data on a graph. The perceptron's brain, all its knowledge, is basically just a single straight line. We call it a decision boundary. It draws this line right through the data to try and separate all the is my mom dots from the is not my mom dots. So what happens when it makes a mistake? It just means one of those dots is on the wrong side of the line. And the learning process? It's literally just moving that line. It tilts it, it shifts it, just enough to get that one wrong point onto the correct side. It's learning one mistake at a time. But there's a catch. This simple method of just nudging the line around for every little mistake, it can be a bit aggressive. The updates are so big that the whole model can become really unstable. I absolutely love this quote someone came up with. Because the algorithm makes these huge corrections based on just one single mistake, that decision boundary line can jump around like crazy. It can even jump right over a perfect solution without ever landing on it. Yeah, it's definitely not a smooth ride.
So how do we fix that? Well, the solution is this really elegant, simple trick that smooths out all those wild jumps. It helps create a model that's way more stable and reliable. It's a tiny change, but it makes for a much, much smarter machine.
This technique, it's a type of regularization. Instead of just grabbing the very last position of the line after all the training is done, we do something clever. We keep track of every single position the line was in during the whole process, and then we just average them all together. And this has a fantastic side effect. It cancels out the noise. Any of those unreliable features that were making the line jump all over the place, their influence gets averaged out, pretty much down to zero.
Okay, so we've made our Perceptron smarter. We've made it more stable. But even with this awesome upgrade, there is one deep, fundamental flaw, a limitation that a single Perceptron can just never, ever get past.
And here it is, the fatal flaw. No matter how much data you give it, no matter how long you train it, a single perceptron is what we call a linear classifier. And that's just a fancy way of saying all it can ever do is draw a straight line. That's its only trick. In higher dimensions, it's a flat plane, but you get the idea. It can only cut the world in two with one straight chop.
And that means it is completely, utterly powerless against certain kinds of problems. Take a look at this classic example. It's called the XOR problem. Just look at it. There is no way at all you could draw one single straight line to cleanly separate the dark circles from the light ones. It's impossible. And for a perceptron, that means this problem is totally unsolvable. You know, this exact limitation, the fact that it couldn't solve these nonlinear problems, actually led to a period known as the first AI winter, where funding and interest just dried up, but it also forced researchers to get really creative. It left the entire field with this one massive question. If one straight line isn't enough, how do we teach a machine to draw a curve? And the answer to that question? Well, that's what gave us modern deep neural networks. And that's a story for our next explainer.